Hi, John here. In this video we're going to look at the centrifugal pump and I'm going to explain to you how it works. So let's dive in. Let's do a little spin. Here is the exterior view of the pump again. And if we spin around the other side, we've got a cross section. Now I'm not going to go through the terminology and the components because we've covered that in another video. But let's just go through the components that we actually need to talk about. And the components are the impeller and the volute casing. So how is it that the centrifugal pump works? You can see from the design and the animation that the pump's construction is quite simple. Essentially, we've got an impeller rotating within a volute casing. And as it rotates through the liquid, we're creating pressure, and this pressure differential, that is the difference between the suction side of the pump and the discharge side of the pump, is what causes the liquid to flow. Well, in order to understand how the centrifugal pump works, we need to have a very quick look at some of the theory. So let's first pull up an open centrifugal pump impeller. So here we are, we're now looking at a centrifugal semi-open type impeller. So the type we saw earlier was the enclosed type, and this one is a semi-open type or the semi-closed, depending on how you want to look at it. As you can see, it is rotating in a clockwise direction. I'll give it a little spin. And we can see also that there's a shaft in the middle of the impeller and a shaft key which connects the shaft to the impeller itself. The suction side of the impeller is this middle area here. That's what we call the eye of the impeller. And as we draw the liquid in, we're going to create a negative pressure at the eye of the impeller. And then we're going to throw the liquid outwards radially away from the center of the impeller towards the outer periphery of the impeller. The reason the liquid is thrown outwards radially away from the center eye of the impeller is because of the friction between the impeller and the liquid. As the impeller moves, some of this movement is imparted onto the liquid. And because the impeller is rotating from a center axis, the liquid has a tendency to be thrown outwards away from the eye of the impeller. Now the force that causes this is known as centrifugal force. And because this type of pump uses centrifugal force, it's called a centrifugal pump. If you've ever driven around a corner very fast in your car, you'll know that if you're driving around a corner and turning into the left, you have a tendency to be thrown outwards to the right. And this is centrifugal force. Now the impeller does the same job, although on a much smaller scale. It rotates very fast from a center axis of rotation, and the liquid that is drawn into the center is thrown outwards to the side, radially away from the eye of the impeller. This centrifugal force gives us a large increase in velocity, which we can later turn into pressure. So let's just pause the animation and I can show you the flow path of the liquid. So the animation is now paused. Zoom in. Our liquid would come in fact let's just do it as the liquid would flow. We would flow into the middle like so. The liquid is then thrown outwards radially and it's going to go between these two veins, or between a set of veins I should say, between a pair of veins. And then it's going to flow up along here, it's going to be thrown outwards and then it's going to leave the impeller. So let's do it this time, but this time we'll just add some arrows to mark the flow. So as you can see, now the liquid would flow out radially, and as it does so, as it flows out through the channels, the flow path area is going to gradually increase. And as it increases, we're going to get a reduction in velocity and an increase in pressure. So that is essentially what the centrifugal impeller is doing. It's converting velocity into pressure. And that's what we need in order that we can get flow. But let's now have a look at the theory behind this, and the theory behind it is known as Bernoulli's principle. Okay, so here we are. This is our Bernoulli principle simulator. You can see we've got an underground pipe. We can assume this is going to be an underground water pipe. I'm going to turn the dots off, but you can see that the flow is from left to right. And if we take our speed gauge, we can put a speed gauge on the pipe, another speed gauge here, and we can see, in fact I'll raise these up just ever so slightly, we can see that at these 2 points the flow is constant and the speed remains the same irrespective of where we put our speed gauges. We can do it like this. And this makes sense because we've got a constant flow. Now this constant flow is required in order to apply Bernoulli's principle. Bernoulli's principle states that if we have a constant flow and we change the flow path area, then we get a corresponding change in pressure and velocity. So let's put the theory to the test. I'll take my pressure gauge and I'm going to install it. In fact, we can install it roughly here. So it's slightly in front of the speed gauge in relationship to the flow. And I'll take my pressure gauge and I'll try and do roughly the same thing again. See, it's a bit further down here. And there we go. We've got the exact same pressure and the exact same speed. So Bernoulli's principle states that if the flow is constant and we adjust the flow path area, then we'll get a change in speed and pressure. So I'll extend the pipe and I'll make the pipe a little bit bigger in diameter. And we can see already the speed has dropped. It's now 0.7 meters per second instead of 1.6. And the pressure has increased. Can do it also here. Again, the speed has dropped 0.4 meters per second and the pressure has increased again. So we know that if we increase the flow path area, we get a reduction in speed and an increase in pressure. And that's what Bernoulli's principle states. If we go the opposite way, we can try and make the flow path here slightly smaller. In fact, I have to extend it a little bit because otherwise we don't get our pressure reading. And we can see that the speed on the left is 0.4 meters per second, but the speed on the right has increased. Let's just take this handle, reduce it. And now we can really see that if we create a massive restriction in the pipeline, then we get a huge reduction in pressure and a massive increase in speed. You can see here our speed is, or was, about 5.6, 5.7 meters per second. So a quick recap. If the flow path becomes larger, the speed reduces and the pressure increases. If the flow path becomes smaller, the speed increases and the pressure reduces. And you can see we've got quite a lot of pressure reduction when we compare both the left and the right. So let's now go back to our impeller and apply Bernoulli's principle in order to figure out how it works. So here is our impeller again, and we can see that the flow path area increases as the flow flows out radially away from the center of the impeller, and we know now that this increase in flow path is going to cause a reduction in velocity and an increase in pressure. And that is essentially how a centrifugal pump works. Now after the impeller, usually there'll be a volute casing or a diffuser, but the concept behind the design of the volute casing and diffuser is the same as for the impeller. We know that we need to increase the flow path area in order to increase the pressure. And as you can see on the diagram now, the volute casing does just that. As the liquid is discharged from the impeller, it's going to flow around the volute casing and we're going to get a reduction in velocity and an increase in pressure. And that is essentially how a centrifugal pump works. There really is nothing more to it. So let's go back to our main centrifugal pump model and we'll do a very quick recap. So here we are, we're looking at our centrifugal pump. Let's imagine we are the flow. the centrifugal pump impeller is spinning, we're going to be drawn into the impeller eye because it's creating a negative pressure. So we've been drawn into the impeller eye. We're now going to flow out of the vanes. We can see the vanes just on the inside of the impeller. I'll see if I can actually get through the vanes. It's going to be quite tricky because the whole thing's pretty tight. So we're flowing through here, through, further, further, further. We're being thrown out radially, and then we're going to exit the impeller and go to the volute casing. Now we're inside of the volute casing, and look, as we are thrown out of the impeller, we enter the volute casing and notice how much more space there is as we move towards the discharge pipe. That's this pipe that we can view at the top of the screen, compared to how much space there is on the opposite side. You can see it's getting continually narrower if we wanted to flow back the other way. So down this side here is quite narrow, but the diameter of the volute casing is gradually increasing until we get onto this side here. And that means our flow path is gradually getting bigger, and all of a sudden we've got loads of space, and that means the velocity is decreased and the pressure is increased, and then we can move on our way through the rest of the system. So that's it. That is how the centrifugal pump works. If you haven't checked out the other two videos on centrifugal pump impellers and centrifugal pump components, then I recommend you do that now because those videos are also really useful. And if you like this video, please do like it or share it on social media. It really does help me out and allows me to produce more and more content. This video lesson is taken from the Introduction to Centrifugal Pumps course. So if you like the lesson, then check the video description area, and there you'll find a link with a special discount price coupon. And if you click on that link, you'll be able to purchase the course at a discount price. Thanks very much for your time.